This lesson is on increasing and decreasing functions and finding relative extrema using calculus instead of graphing. So now we're not going to even have to look at a graph to find relative extrema using something we call the first derivative test. The first thing you need to know before you learn the first derivative test is what the definition of an increasing function and a decreasing function is. It's pretty intuitive what they are, but we do want to formally define an increasing function or an increasing function, or a function that is increasing on an interval or decreasing on an interval. So an increasing function, just like it sounds, is a function that's going up. As x moves to the right, the function is going up. If the function is going up, if it's increasing, if it's getting higher, that means that the slope of the tangent line must be a positive number. Therefore, an increasing function, one that's going up, is a function where f prime of x, the derivative, is greater than 0, where the derivative is a positive number. A decreasing function is just the opposite of that, a function that's going down as you move to the right, where its tangent lines would be negative, it would be going down. So the derivative f prime of x is less than 0 for a decreasing function. Increasing function going up, decreasing function going down. Derivative is positive for an increasing function, derivative is negative for a decreasing function, at least on an interval. We usually talk about increasing or decreasing on an interval, on an open interval. There's also a constant function where the derivative is equal to 0. That would be a horizontal line. That doesn't happen too often, but it is possible. Very, very important idea right here. If a function is continuous on an interval, then the only place it can change from increasing to decreasing or from decreasing to increasing is at a critical number. That's the only place it can happen. If it's increasing all the way here, the only place it can change to go to decreasing, that x value where it changes has to be a critical number. It can't happen anywhere else. That idea is vital to understanding how to do this and how to find extrema using derivatives and using calculus instead of graphing. The only place a function can change from increasing to decreasing or from decreasing to increasing is at a critical number. Just because it's a critical number doesn't mean it has to change there, but that's the only place it can change. And we talked about that the other section when we talked about critical numbers. But that is the whole basis for this first derivative test and this method of finding intervals of increasing and decreasing that we're going to talk about next. Some problems will ask you, find all open intervals where the function is either increasing or decreasing. Many functions, especially when you get into larger power functions, polynomial functions, they're going to be increasing and decreasing and increasing, changing whether they're going up or going down. They're going to have some turning points. So this function here, or this problem here says, find the open intervals on which the function is increasing or decreasing. So the original function they give you is f of x equals 5x cubed minus 60x. The only place a function can change from increasing to decreasing is at its critical numbers. So the first thing we want to do is use this idea and find critical numbers. Critical numbers are defined as values of x where the derivative of the function is either 0 or undefined. So the first thing we do to find open intervals of increasing or decreasing is derive the function. 15x squared minus 60. Then we want to take that derivative and set it equal to 0 to find where it equals 0 and find where it's undefined. If it's a rational function or if it's a radical function, it can be undefined in certain areas. This function here, power function, will never be undefined. The derivative will never be undefined. So it's differentiable everywhere. So we just have to worry about where the derivative equals 0. So I factor out of 15. You're left with x squared minus 4. Use the difference of squares to make that x plus 2x minus 2. Therefore, your critical numbers, f prime of x equals 0 at x is plus and minus 2. So you know, everywhere on this graph, everywhere from negative infinity to positive infinity on the x-axis, 5x cubed minus 60x is continuous differentiable. So it's either increasing or decreasing everywhere. It's got to be either going up or going down everywhere, except at negative 2 and positive 2. It's doing something else everywhere else. The only place the derivative is 0 is at plus and minus 2. So what we're going to use to help us find these open intervals is we're going to use what's called a sign chart. A sign chart is basically a number line. So you use a number line representing the x-axis. The only points you're worried about, again, the only points that matter are the critical numbers. -2 and +2 in this case. So you make a number line, you put -2 over here, +2 here. If there were 3 or 4 critical numbers, you would put them on the number line in numerical order with a little bit of space in between. We know that at -2, the slope is 0. We know at +2, the slope is 0. We know everywhere else, the function is either increasing or decreasing. Well, the definition of an increasing function is its derivative is positive, is greater than 0. The definition of a decreasing function is derivative is negative or less than 0. So we have 3 areas to look at. We want to look before -2, because everything before -2 must be doing the same thing. Between -2 and 2, because from here to here, the function has to be doing the same thing. And after +2, because again, it has to be doing the same thing. These are the only spots it's not increasing or decreasing. So, you know, anywhere on those 3 intervals, the function is either increasing or decreasing, and it's doing the same thing the whole way. So what we need to do is pick a point, pick a test value of x. I want to know. I know it's doing the same thing over here, so you want to pick a number to the left of -2. I pick -3. Realize that you're looking to see if the function is increasing or decreasing. So all that matters is the sign of the derivative, whether the derivative is positive or negative. The actual value of the derivative doesn't matter, as long as you know if it's a positive number or a negative number. So I take -3, and very important, I plug -3 back into the derivative to see the slope of the tangent line. I know if it's going up or if it's going down. -3 squared is 9. 15 times 9 is 135. Minus 60 is 75. So we know this is a positive number. Even if you couldn't do that math in your head without a calculator, you could know that -3 squared is 9. 15 times 9 is over 100. So minus 60, you'll still be left with a positive number. And as you'll see down here, I don't write what the value is. I write the point I tested and whether the derivative is positive or negative. So this derivative is positive here. Actually, as you get good at these, as you do more and more of these, you normally won't write the number that you pick. You'll pick a number and you'll just write a plus sign or a minus sign, figuring out if it's a positive number or a negative number for the derivative, figuring out if it's increasing or decreasing. Between -2 and 2, 0 is always a good number to pick. Plug in 0 into the derivative again, see what the slope of the tangent line is. 0 minus 60, negative number. Again, the sign's all that matters. It's doing the same thing all the way here. Pick 3, write the same value because it's squared, positive number again. So you use this sign chart knowing that the critical numbers are the boundaries. Before, between, and after, it's doing the same thing. The critical number is the only spot it can change. So I know anywhere between -2 or before -2, it's doing the same thing, so I pick an easy number to work with and evaluate it in the derivative to see if I get a positive or a negative number. So using this sign chart, and I copied it over here, same sign chart you just had, that means that this function is increasing on the interval -infinity to -2. From all the way over here, all the way up to -2, the derivative was positive, so the function is increasing. And the same thing from +2 to infinity. The function is decreasing between -2 and 2. So I write that separately down here, decreasing on that interval. Make sure you realize these are open intervals. We don't use the brackets to close them because at -2 and 2, the function has a horizontal tangent or an undefined tangent, some other problems you'll get to. But you're not counting these boundary points. It's before, between, and after, not at those points. And you always have an open circle at infinity because you can keep going. You can't close infinity. So you use a sign chart to find intervals of increasing or decreasing, and you write them as open intervals. Find critical numbers by deriving and setting the derivative equal to 0, or where the derivative is undefined. Use a sign chart to test values before, between, and after those critical numbers. You test those values in the derivative to see what the slope of the tangent line is, to see if the function is going up or going down. And you're only worried about the sign of the derivative at those points. You're not worried about the actual value. If it's positive, that's good enough. If it's negative, that's good enough. Last thing, we're going to use this same idea and add one more step to it. We're going to use calculus to determine where we have relative mins and relative maxes, relative extrema of our function. Instead of having to graph it and look at it, we're going to use calculus to find the exact x values, where you have your relative extrema. So we're working with calculus to get a picture of the graph. And relative extrema are important. Highs and lows on a graph are important for us in order to graph these. Remember, 2 lessons down the road, we're going to be graphing functions without using a calculator. So being able to identify where it's increasing and where it's decreasing, and where you have a relative extrema, or a relative max, or a relative min, are very important things to help us get the overall picture of the graph. Remember, relative extrema, relative max, and min can only occur at critical numbers. So you're going to do the same thing. Derive, find out where it's 0 or undefined to find your critical numbers. Test your sign chart. Plus, minus, plus, increasing, decreasing, increasing. The last thing is to think a little bit. I like to draw little arrows here. I know on this whole interval the function's increasing, so I drew an arrow going up to the -2. After -2, between here, the function's going down, so I drew an arrow going down, a little piece of a segment going down. Then afterwards, I went back up again. Now we've got to think about what this means. If the function's increasing before -2, then decreasing after -2, it's going up, then coming back down, that must mean if you went up, then back down, you have a relative maximum at x equals -2. And then if you're going down here, coming back up here, well, you must have a relative minimum at x equals +2. So you write that down, relative max at x equals -2, relative min at x equals 2. Sometimes some books or some tests might ask you for the value of the function. It might ask you to say, where is the relative max? You would say -2, and then you have to plug it back in to the other equation to find the value of y. Most of the time, you're just looking for the x values, but if they ask you for the point, remember you would plug this back into the original equation to find your y value. And then if you look at the graph of this, you see the graph of the original function. At x is -2, we did have a max. We did have the top of a hump. Max at x equals 2, a relative max. And then at x equals +2, that's the bottom. So your x value for your relative min is also correct there. Sign charts, little lines to help determine. And then identifying the x values where these happen. First derivative test is used to find relative extrema, relative max and relative min. Find the derivative, set it equal to 0 or find where it's undefined, find your critical numbers, set up your sign chart. Test points in each interval, draw your arrows to see, and then you'll be able to determine whether you have a relative max or a relative min. If you need the actual point of the max or the min, then you plug the value, the x value, back into the original equation. Don't get confused with where you plug the values into. All right? If you want to know what the function is doing, whether it's going up or going down, you need the slope of the tangent line, so you plug x into the derivative. If you want to know the value of the function, you want to know the height, the actual value, the y value, then you plug that x value back into the original function.